We are a consortium of Earth observation specialists working for the European Space Agency.
The framework in which we operate is twofold. The first guiding principle is the United Nations Sustainable Development Goal 11. Make cities and human settlements inclusive, safe, resilient and sustainable. The second framework is the Project Implementation Strategy in international financing institutions like the World Bank and other development banks.
Our aim is to extend and improve the use of satellite data for the monitoring of indicators in order to reach Sustainable Development Goal number 11. We also want to facilitate international development work in a globally consistent manner by using Earth observation data and methods.
We have covered 32 cities around the globe with a total of more than 510 products and 11,000 square kilometers mapped. Our basic products comprise status and evolution of urban extent, as well as land use and land cover and its change over time. More specifically, targeted maps include slum maps, maps of open and green spaces, building footprints and heights, infrastructure, as well as hazard and risk maps. Based on these maps, we generate spatial analytics and the before-mentioned indicators for SDG 11.
These tools are very much relevant because they provide evidence.
In general, the preparations of bank operations take several years, but in these cases, it only took around 6 to 8 months for the preparation. Thanks to the whole analytics, maps, and data evidences. The best part is that it was helpful to communicate with various stakeholders on the ground.
I'm Manuela Hirschmuggel. I'm from Ioneum Research in Graz in Austria, and I'm moderating this webinar series and organizing it. Today we have 4 speakers, and I'm very, very glad that we have 2 speakers from within our project consortium, and which makes me even more happy, we have 2 guest speakers. So Tomas Soukup and Kolomaznik are from GISAT, from within our consortium in the project, and we have Amit Patel from the University of Massachusetts, Boston, who will take over part of this presentation, and Christian Borja-Vega from the World Bank Group, who will give us the user perspective. Today's topic is slums, informal settlements, basic services, access to basic services, and we'll start with an introduction to the products which we derive within our product, and the whole context, how this product was set up, which will be given by Tomas. Then the mapping of slums by remote sensing will be explained by Jan, followed by Amit's talk about predicting slum dwellers' deprivations from space. And finally, Christian will conclude on how type of data can be used and how the user perspective is from the World Bank Group side. And this will all then be followed by questions. I will make Tomas presenter.
Talk today about space application support in the context of informal settlements, or let's say slums. Before we will jump into more technical details, I will just briefly introduce you the whole activity, so it's clear, understood the context of the work done. And I apologize to those who attend the whole series for a little repetition, but I think it's important to understand this context. So I have already mentioned space, so I will start with spacelight. So just to highlight the driver or enabler of our whole activity. There is currently a strong European space program called Copernicus, developed in last decade. And it is supported by ESA and EU with a growing constellation of the Sentinels Earth observational satellites. And with this capacity, which is, by the way, free and open, is the aim to support really the global challenges, including the sustainable development, what is the topic of today. So based on this development, the ESA collaborates with a number of international financial institutions and also multilateral development banks already since 2008. And basically, ESA is trying to explore how to use this space capacity in the most effective way, and also to achieve the expected impact of all these investments. So ESA has currently some memorandums of understanding or the secondments with number of banks. And basically, our activity, which we present today jointly, is in the frame of this ESA collaborations. The work which is presented today was in particular done in project EO4SD for urban, which is already in place from 2016. And this is another activity in this direction, in this general direction. But in this time, this project is a bit bigger, both in size, because it takes almost 8 years, but also in bigger in a sense of ambitions. We basically, our ambitions and objective is really to improve the understanding of the EO used in these institutions, but also to mainstream really to use these potential information sources in a standard, let's say, working practices, and also to find the way for some systematic financing on these activities. So you see the consortium led by GAF, and GSAT is a partner of this consortium. So we basically start providing the standard products and services. We have a portfolio of such services, which the word standard means that these are not one-time ad hoc productions, but the production which is based on certain qualities. Let's say based on user requirements, tailored for some specific support, harmonized from the point of nomenclatures, standardized, so the same methodology is used. This is very much important for comparison, for example. We have very stringent quality procedures, and we also document clearly how the stuff is done. And one of the products in this portfolio is product for informal settlements, and that's basically what we are discussing today. We have this standard product where we look for state of the slums, for their evolution in time. We are able to monitor the multiple characteristics, provide some specific typology. But in the project which we discussed today, we were trying to go even a bit beyond just the data supply. And together with World Bank and with the University of Massachusetts, we try to integrate our outputs from the EO-based slum information monitoring and try to see it from the broader context, integrate it with some bank data, and use it for the deprivation modeling, in this case, on the use case in Dhaka city. So this activity is supported by the Water Supply and Sanitation Global Solution Group, which maybe will be later on mentioned in detail by Christian. And we will see now in my colleagues how it was done in the details in a more technical way. So that's for the introduction, so you understand how we basically, why we did it and what was the goal of this whole activity. So thanks for, and I will give a floor to Jan.
Okay. Thank you very much, Tomas and Manuela. So, my name is Jan Kolomaznik. I'm a colleague of Tomas from GISAT, and in frame of this presentation, I would like to introduce you the slum mapping from Earth observation. The aim of the presentation is to give you basic insight into principles of slum and informal settlement mapping from satellite data. In the first part, I will focus a bit more on theoretical background, while the second part will be quite packed with examples of the results and examples of analytical products derived from these results. At the very beginning, it should be noted that there is no simple and fully universal slum definition available, but generally and mostly widely adopted one is from UN Habitat, who came up with a comprehensive set of slum characteristics. They define slums as the areas with households that are attributed to deprived access to basic services such as water, sanitation, electricity, etc., to overcrowding, which is related to high population density and inadequate living space, to substandard housing, related to lack of durable housing structures, non-permanent materials, and location in hazard-susceptible locations, and to insecure land tenure, which is related to lack of entitlement to legally occupy the land and related vulnerability of the communities. Other definitions consider slums as the areas with high concentration of the poor people living in substandard conditions. And for instance, World Bank is putting an emphasis on multidimensional nature of the slums and spatial context, which is related to localization of the slums within areas affected by urban sprawl or in the context of urban planning. So improving livelihoods of poor people in slums in development world has been recognized as a priority by international development community, and there are really a lot of various slum interventions and upgrading policies that are being implemented at various scales. At the global and country scale, there are comparative city-level diagnostics that can be monitored. Examples are SDG target for housing and slums, or for instance, World Bank's Global City indicators. Both these slum-related indicators are showing proportion of urban population or proportion of slum area on the city area. At the higher level of granularity, there are measures that are aimed at improvement physical and social or economical conditions of slum dwellers. They are called slum upgrading initiatives. And these initiatives very often are facing some problems. These problems are related, in fact, to lack of reliable local data about slum locations and characteristics. Having lack of reliable information about house deprivation, it is really difficult to prioritize the interventions. At the same time, it is difficult to scale up the interventions from pilot study level to the citywide level because of expenses or costs related to ground surveys. And this is exactly the space where remote sensing can give a hand, because remote sensing is in fact bridging this information gap represented by lack of data about urban poor people and their locations. Over the last 17 years, it has been proven by many studies that remote sensing has become recognized tool for slum mapping. It uses archive or up-to-date satellite imagery to delineate the slum extent and to extract the slum characteristics that are visible from this imagery, and by providing, let's say, explanatory proxy variables to deprivation. It is assumed that, and it has been proven by several studies, that there are comparatively different income distributions or deprivation patterns between morphologic slums and formal residential fabric. I'm not going to go too much into detail about methodology. I will give you just an overview. So typically the slum mapping starts with a definition of ontological framework, sometimes referred to as a generic slum ontology according to Coley et al. Basically, it is translation of generic slum characteristics related to slum environments, slum area extent itself, and the objects that are within the slum dwellings, to slum indicators related to detectable image features, such as spectral, textural, structural, and contextual information that is derived from image elements at pixel or object level. As demonstrated in the images at the very bottom, there is high variability in some characteristics across countries, between cities within countries, and even within individual cities. Therefore, some local adaptation of this generic slum ontology is always required for mapping specific cities, and this requires involvement of local expertise. Once having definition of slum ontology and related rule sets, we can proceed with identification of slums and extraction of the indicators. This is accomplished using very high resolution satellite imagery and optionally additional ancillary data like DMs, etc. By image processing techniques like image interpretation, object-based image classification and segmentation, machine learning, or widely used combination of the above methods. Results and characteristics are usually enhanced by open data mining or by incorporation of additional analytical information in terms of hazards and risk levels, accessibility, distance to amenities, transportation, etc. EO4SD Urban Consortium is providing a set of scalable slum products. The standard product is called Slum Extent. It provides us with a location, explicit spatial extent and size of the slum, detected slums in form of polygons. These polygons are referring to physical slum outlines or to so-called homogeneous urban patches, which are the polygons with homogeneous built-up textures, densities that are usually delimited by bounding linear features represented by roads or other linear features. Optionally, the vector polygonal product can be accompanied with additional indicators, additional attributes that are derived using the above mentioned methods. These indicators are divided into several groups. They describe the morphology in terms of homogeneity, shares of different classes, dwelling characteristics showing mean size, spacing between dwellings, their height, orientation, etc. Environmental properties like land use and built-up structures in surroundings, locational ones related to distance measures, accessibility represented by road density, density of connectivity nodes, distance to station or other public transportation units, and last but not least, also by vulnerability measures related to natural, industrial, or transportation hazards. This is an example of multidimensional list of explanatory variables that were derived and provided in frame of the activity that is going to be presented by Amit. The set was derived for each sample represented either by polygon or by buffer around cluster of samples, which were in this case buildings. This is another optional product. It's called Slum Typology, and it is derived from one or multiple attributes or indicators. The advantage of this approach is that thanks to more attributes, we can derive user-tailored custom nomenclatures based on rule-based classification, taking into account target typology. The example on the left is showing typology based on one attribute, density of dwellings, while the example on the right side is showing more complex typology based on multiple attributes and multiple rules. Using archive satellite imagery, we are able to provide information about evolution of slum extent in 2 or more time horizons. And using this information, we can provide attributes like slum or dwelling age and statistics related to gross or net area increase, decrease. We can spatially explicitly identify areas which are subject to slum sprawl or slum withdrawal, and in combination with land use data, we are able to say something about structure of land use classes that were consumed by the slum sprawl, or that were formed, or classes that were formed by the sprawl on side of slum class. This is an example of this information that I have presented that can always be aggregated at various analytical units. So some qualitative and quantitative measures are derived for these custom analytical units, and they usually, well, as a standard in the consortium, we provide this information for administrative units, and we classify several information and provide statistics about several topics like vulnerabilities, proportions of slums on the area or on urban fabric share, etc. EO4SD is also introducing a tool that has been developed by GISAT, and this tool enables its users with online and interactive ways of exploration of the slum mapping results. In this example taken from the screen from the tool, it is shown that the distribution and structure of detected slums can be shown. This information is interactively connected between both graphs and the map or units visualized in the map for each analytical unit. So different analytical units can be mutually compared. At the VART level, various statistics can be aggregated and visualized as chlorophyll maps, and they can be interactively compared between different analytical units as demonstrated. Slum polygons itself may be used as a target analytical units, so that the tool is providing the means to explore the different attributes to detect patterns and clusters with similar characteristics. Example here is showing such an exploration. Such an exploration which is based on analysis of different attributes like built-up density and row density in the surroundings. So individual clusters are detected in different parts of the cities. And this is my last slide where I demonstrate that that different attributes can be normalized and they can be compared using polar graphs, either for all features or for selection of the features. It was to note that the tool provides advanced filtering and selection capabilities. In the second phase of the project, the utility of the tool is going to be evaluated for slum upgrading initiatives. This is all from my side at the moment, and I will give the floor to Amit Patel. So thank you very much for your attention, and I will be happy to answer any questions that you may have at the end of the webinar. Thank you.
Thank you, Jan. And I just want to add that will have a dedicated webinar for this UTAP if you're more interested in. So we go on with Amit Patel's presentation. Amit, the floor is yours.
Thank you, Manuela. This is Amit Patel from University of Massachusetts, Boston. Apologize for my muffled voice. I have really bad cold. It's Arctic winds here and chilly, but I'll hopefully be able to deliver 10 minutes. So what I'm going to do is provide a motivation research goals for this part of the task that we were doing, and then introduce you the data source, particularly the household surveys, since you already heard about the Earth observation data from Jan. And then we will present a model that predicts household level housing deprivation in the statistical model. So our motivation was that for developmental project planning and prioritizing the areas where we need to invest the most, and policy making requires us to do that, either to select most deprived cities or within a city most deprived slum. And often data is not available to do that part, and that's where, as Jan suggested, remote sensing can help. And we were thinking. Remote sensing often focuses on identifying areas and neighborhoods because they are mostly morphological information. But what if our developmental project required us to identify most deprived households? Can we detect household level deprivation from space? And that was the key motivation, and that could result into getting the preliminary sense of deprivation on the ground without going on the ground, which is often a problem when we are doing the project formulation. So we decided to see if all the information that we capture from satellite images, can it predict household level realities that we knew from another survey. So we combined those two data to answer some of these questions. That let's identify most deprived areas, but more importantly, most deprived households from space. And such an endeavor could also help us if we are going to do further ground level surveys, then we can use this as a baseline as kind of universe from where the sampling can be done. So if we know that we want to have a representative sample based on deprivation on water access, for example, if we had some kind of prediction a priori, then that can be used as a sampling frame. So that was the kind of background. In an overall picture, what we did is took the household surveys, which are the outcome variables of interest related to household level housing deprivation, and then combined that with data from Earth observation that Jan just described, like neighborhood level characteristics, etc. And then we use that integrated data to run regression analysis where we try to predict household level housing deprivation from Earth observation data in a regression framework. And such a predictive model can then be used to predict deprivation for the entire city, even out of sample. And that could then be used for policymaking or planning, which Christian will talk about more. So we chose Dhaka primarily because it's one of the fastest growing mega cities in the developing world, and there was an opportunity for water general practice and other general practices to be partners. And it was also Dhaka city officials were open and interested in improving basic services in informal areas. And then there was, most importantly for us, there was availability of relevant data from WASH poverty diagnostic that the World Bank has carried out. And ESA has shortlisted urban development as one of the pilot themes that Thomas talked about. And to our knowledge, there was no single attempt to predict multidimensional housing deprivation using remote sensing as an input. So I'll skip the Earth observation data part that Jan has already described and talk about household surveys that we used to combine with Earth observation. This is from WASH Poverty Diagnostic Surveys in Dhaka, and it is there There were 2 rounds in Bangladesh with urban informal settlements baseline survey. First was in May 2016, where 600 households were surveyed in 63 slum communities. That's the data we used. And in June of 2016, there was another round of 6 slums with 600 households with more detailed data. That's the part we did not use for the remote sensing part, but we have some comparative statistics on that. So the sampling from frame for this data collection that Water Practice did was to first take slums and divide them into small, medium, and large communities and take the sample from each of them in proportion. So there were several questions asked on the survey, but what we are focusing on is the housing deprivation. So we'll talk about what housing deprivation means. And as Jan suggested, there are several definitions, but we stuck with the UN Habitats 2002 and then updated 2010 definition, which basically focuses on 5 elements of housing. So if you lack access to durable housing, if there is overcrowding and there is no access to water or sanitation, and you lack security of tenure, then that household is deprived on one of the 5 elements, and it could be considered as a slum household. So here, the important thing is that we're talking about individual households, not the entire community. Of course, the aggregate community level data can also be obtained in the same fashion. And we developed a new index called Slum Severity Index, which is a simple additive measure. So if a household lacks all 5 housing elements, that's most deprived. And if household is only deprived of 1 element, then that's less deprived. And this is important because if we are doing community level interventions, then this might not matter. But if you are, let's say, trying to provide a public toilet, that's community level intervention, and all you need to do is identify that slum. But if you're doing, for example, an intervention where you want to provide voucher to individual households who are most deprived for, let's say, building an individual toilet, then you want to identify households within a slum. And so we tried to operationalize this for household level as slum severity index for each household, and it varied from 0 to 5. In this case, we used all 5 of UN Habitat elements, and then we added electricity as a measure for access to energy. So our index was varying from 0 to 6. And here it could be also, this measure could be stretched because now we're talking about levels of access. So access to water is not 0, 1. It's also access to water within 30 minutes, access to water on premise, etc. So if you want to stretch this variable, it could. It's flexible, it's additive. So here is what we found from the surveys. Access to water, there were 3.6% households who did not have it. Electricity, 3.6%. And sanitation, 9.88% people did not have access to sanitation. So as you can see, these are predicting rare events in some cases in electricity and water, but sanitation is where the deprivation is higher. In the overcrowding, quite a lot of people, 74.5%, 58.2% felt insecure, and so on. Sorry, the 58% had temporary structure and 3.6% felt insecure in their housing. So this is the basic descriptive statistics for our dependent variables in regression framework. And finally, the slum severity index, its distribution is that there are quite a few, like 8 or 10% households who are deprived of 4 elements. And there are some who within slums who are not deprived of anything. So there's quite a heterogeneity within slum households that we're trying to capture here. So as I suggested, the regression framework is very simple. We have 0, 1 variables for each access indicators for water, sanitation, permanent structure, etc. And we also have a continuous, rather than ordinal variable for slum severity index and our input data. is purely coming from Earth observation that Jan described. So what we are trying to do is, can we predict those household level information that we already know from the ground using remote sensing data alone? So just to give you an example, if we can see the average dwelling size in an area, could that be a good predictor to tell us whether there will be a toilet or not? And our thinking is that if a household has very small footprint, then it's quite likely that they are going to use that precious space for living, cooking, and sleeping, and they're not going to build an individual toilet. There are also locational characteristics. For example, if you are on a hazardous location, it's quite likely that the city government would not invest in piped water or sanitation systems. And those could be telling without really going underground, because those observations can be made from satellite images. So that was our basic understanding behind building such a model. So it's not quite causal, but can some of these things explain what's on the ground? So some of the things we found was quite true. So for example, if we take distance from central business district, which is a locational characteristics for a slum, we see that the probability of lacking sanitation goes up as you go further, which is kind of supporting what we know from theory that the slums are peripheralizing, which means more and more poor people are being pushed out to the peripheries where there are no services, and that's where they can afford to live. Similarly, we also see that when slums are dense, they are more likely to get sanitation. This might have to do something with consolidation of communities. The older communities get consolidated and may be able to ask for their rights from the city government and so on. So some of these things are kind of in line with what we know from theory, but we also observed them on ground in our bivariate analysis. Then we, of course, did the multivariate analysis with all the Earth observation data, and we saw how it affects our outcome variables, and they are like 0, 1 for lack of access to water or not, and an ordinal slum severity index. And quite a lot of predictors were useful in predicting this deprivation. So for example, distance to central business district is a strong predictor for many housing deprivations. Further you go, you don't have access, and several neighborhood characteristics, like if it's a dense environment physically, then you're likely to see fewer deprivations and so on. So our main limitation was that this is an exploratory study with very small sample size, and we have done aggregation at the slum community level to run Poisson regressions, but ideally we would like to have household level locations for a large data set and then triangulate these results to see where it takes. I'll stop here. There are quite a lot of possibilities here in terms of integrating data, but I'll move on to Christian, who can tell us more about how it can be used in the practice. Thank you.
Thank you, Amit, for this really interesting presentation. Christian, the floor is yours.
Thank you very much. And thanks everybody for being here. I'm very glad to be part of this webinar and presenting some of the results of our study. So we have talked about the methodology, the genesis of this study, and right now what we need to convey to you is some ideas about why these collaborations matter, why this kind of research matters to our daily use in whatever institution you are. Particularly, I'm going to focus on some examples that we have used, where we have used Earth observation tools to help us better implement large-scale investment programs, for instance, by improving targeting, by understanding very well, like Amit was saying before, what's happening on the ground, what sort of characterization and key determinants can facilitate the implementation of projects, and therefore maximize the effectiveness of those projects. We have seen very big interactions between the urban configuration and the way water, energy, transport services are also present or not. And those are important features because when we understand how the urban conglomerations are moving or are shaped in a given space, we can identify some binding constraints, physical binding constraints that allows us to see whether water, energy, or transport services are feasible to be implemented. No? The analytical work in this case and in many other cases that have been applied by combining different sorts of information with Earth observation have helped us to leverage different operations. We have seen that for instance, in the analysis of slums in Metro Manila, which was a project that used Earth observation and extracted several points in time and revealed some trends and patterns in slum formation, enabling a highly accurate mapping of informal settlements, and that facilitated very much the implementation of a large-scale slum improvement program. That kind of leverage is strategic for institutions like the bank or bilateral agencies or donors, so that they can use the findings of Earth observation data analysis and then validate in the field what's happening to make decision making more dynamic and more relevant to the context where we are actually intervening now. The prioritization and targeting of programs is an important point that is more and more relevant for local governments and specialized agencies in charge of delivering, for instance, water projects, energy projects, or simply slum upgrading interventions. And these tools are very much relevant because they provide evidence on how can we use more effective limited resources to meet the demands of city planning and to also meet the ever increasing demand of basic public services. No, we have an example of an approach that was used in African cities, where we produce several land cover maps derived from high resolution satellite imageries. And in those cities that included Addis Ababa, Nairobi, Dar es Salaam, Dakar, and Kigali, this satellite imagery was used to measure footprints of cities and distinguishing between the urban and non-urban areas to dig deeper into measures of land cover types within the city. With that, how can we use that information? Well, local governments, city mayors are using that to precisely organize better and target better expansion of housing in certain areas, no? Or they can understand better where it's feasible to and cost effective to introduce basic services, no? That is facilitating a lot also our work as a development agency, and that's why those kinds of research inputs are very important for leveraging, prioritizing, and targeting our programs. Over the long term, just to conclude, we need to develop a technical expertise market to actually make this analysis of Earth observation imagery more systematic within our programs, our development initiatives, so that we can start spilling over all this technical support in developing countries as well, so that they can learn about these options and they can implement them and strengthening their decision-making systems. Also, it's very important to strengthen channels for collaborating directly, so that governments and local agencies can understand the value of these and can actually contribute in developing further ideas on how to use effectively these options. Many times we need to expand the knowledge curve, frontier curve, with developing countries so that we understand very well what are the needs and what are the capabilities of contribution of these Earth observation tools. No? And finally, an important point over the long run is that these types of tools helps us identify economies of scales and blending finances with other partners for complex tasks. No, intervening in slums, it's quite complex. There are many competing demands among sectors, and we need to understand what sort of dynamics are being responded by these types of analytics, and then blend some initiatives through finance, through analytical support, to technical assistance, so that we can take the maximum cut of these tools within the development process of an urban area. You know? And with that, I want to thank very much everybody, and we're open for your questions and your comments on these presentations. Thank you very much.
Thank you. Thank you, Christian, for your view from the user side or from the World Bank side and what Earth observation can contribute. I think it was very interesting.